This short video will introduce the phenomenon of surface wrinkling. It will define and explain the types of wrinkles observed in soft materials, and a video demonstration of wrinkle formation will then elucidate the physical basis for surface wrinkling. The first natural question then to ask is, what is wrinkling? Loosely, wrinkling is defined as surface profile changes due to material deformation. Common examples that we might see in everyday life include skin wrinkles or fabric wrinkles, where some underlying motion causes a wrinkling pattern to occur in this macro scale material that we work with. In more technical parlance, we define wrinkles as having repeated surface features and a specific wavy surface shape that's described by a sinusoid. On the right-hand side, we see that type of shape in a cross-section of a soft material block that's being compressed, and we see this surface profile of a wrinkle show up. On the left-hand image, we see an experimental result where the surface profile is observable with repeated wavy type surface profilometry. Now this seems all pretty abstract at this point, so we'll move on to answer the question, why does this matter? With the examples presented thus far, it might seem like wrinkling is just a petty annoyance, but it's actually very important to many fundamental systems that we rely on. For example, the brain and intestines are both very wrinkled in order to fit as much surface area as possible into a very confined space, and they grow that way specifically with this intent. In some engineered systems, wrinkling is a failure mode that we seek to find a way around, but in many it's also very useful. For example, in soft robotics and bendable electronics, we can use wrinkling to either improve frictional characteristics for grippers, for example, or to allow independent parts that have to remain fixed to be able to bend with respect to each other in a repeatable way. Also, by wrinkling the surface of an electrode in a battery, we can vastly improve the surface area and thus charge density that the battery has. And of course, there are many other examples within engineering that we can see wrinkling as an important system that we can utilize. Having now defined wrinkles and discussed why wrinkles are important, we turn to three ways that wrinkles can arise in physical systems. The first of these three ways is through constrained volume change, where the volume of the system changes while the surface area remains relatively constant. For this case, we use the example of a pea shown in the upper right-hand corner, where initially the pea is full of water, the exterior is smooth, and then as water is removed, the surface area stays the same, but encompasses a smaller volume, such that wrinkles have to form on the surface in order for that surface area to remain the same. In the second case, we form wrinkles if we have a hard layer on a soft bulk. For example, we have soft polymer substrate that's been treated with a very hard surface layer, and we compress that and we get these wrinkles shown in the bottom left-hand picture. The skin wrinkling is a similar phenomenon where the skin is a hard layer on a soft tissue substrate, and as you articulate, you can see that the skin wrinkles. In the third case, we have mismatched deformation systems, where initially one part of the system is stretched and the other part of the system is then layered onto that. So, for example, in the bottom right-hand image, we have rubber where the orange was initially stretched and the blue was attached to that while it was stretched, and then the stretch was released. And this causes wrinkle formation. We will now move on to show a short video of the wrinkle formation process on a polymer block. In this video, we see an experimental setup that consists of a block of soft polymer with a hard film on the surface that's being compressed. As the compression continues, we see wrinkling start to occur on the surface. This wrinkling is due to competition between the different energetic states in the polymer block and in the hard film. The hard film wants to wrinkle, buckle as it compresses. You might think of this as if you put a piece of paper on your desk and you squeeze it. You're not going to be able to squeeze it successfully. It's always going to fold. Similarly, the hard layer on top always wants to fold. Also, the block wants to remain with a smooth profile because a smooth profile is the most energy-conserving profile. So there's this competition between the surface of the block wanting to remain smooth and the hard layer wanting to buckle that results in a wrinkling phenomenon on the surface of the block, which is what we associate with this surface wrinkling phenomenon that we set out to describe. In summary, wrinkles are sinusoidal surface characteristics that arise due to either constrained volumetric change, modulus mismatch under compression, or initial stretch mismatch. They are widely useful in engineering systems and fundamentally important to many biological systems.